Namaste. Welcome to the lecture series on the subject Basic Thermodynamics. This is module 4 in that part 2, Pure Substances. Lecture number 3. Myself, Dr. Satheesh Kumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Pantwal. So the content for this topic are HS diagram or Mollier chart, property tables, dryness fraction, throttling calorimeter, combined separating and throttling calorimeter. So let us study the HS diagram or the Mollier chart. So this is the enthalpy entropy diagram. Now already you studied the phase change of a pure substance. So you know that the compressed liquid, when heating, it goes to the saturated liquid point, then the phase change process, then it becomes saturated vapor, then finally it becomes the superheated vapor. So here this region, so this is the, here it is written as L, so that is the compressed liquid region, and this is the two-phase region, and this is the vapor region here. Now here in case of HS diagram, so the critical point comes around somewhere here, and this line is the saturated liquid line as it's marked here, and this side, that is above critical point, you can see this line here, you see that is the saturated vapor line, and these are the constant pressure lines, and these are the saturated liquid points where for these pressure, various pressure lines, okay, and all these lines connected to make the saturated liquid line, and these are the saturated vapor lines, and all these lines are connected to the saturated vapor line. So these are the constant pressure lines in case of HS diagram. Okay, this is the entropy here. So this is the entropy of the saturated liquid. So this is the entropy of the saturated vapor here. Okay, now so these are the constant pressure lines. So in the superheated region you have also the constant temperature lines, because in order to mark the point for the saturated vapor, you need the pressure as well as the saturation superheated region. If you want to mark a point in the superheated region, sorry for that, so you need the pressure as well as the superheated temperature. So then only you can locate the point. Now this chart, it is available in your thermodynamic data handbook. It's a big chart. It is stick to the last inner cover of your thermodynamic data handbook, and that looks like this. So this is the Mollier chart which is available in your data handbook. So here you have the saturated vapor line. You see this thick line, so that is the saturated vapor line, right? So point all along this curve is the saturated vapor point. So here all these lines, you can see, these are the constant pressure lines. You see these lines are the constant pressure lines. So these pressure values are marked here. So I'm not able to read that. It's 0.05. I can see something here, 0.1. Okay, see, these values are marked here. So for given pressure where it intersects this constant pressure line intersects the saturated vapor line, so at that point you can find out entropy as well as you can find out enthalpy. So enthalpy you can measure either from the right side or the left side. Even the entropy also you can measure from the bottom axis or the top also you can measure. Now suppose if the steam is in the superheated region, then along with this pressure, so you also should be given the temperature also. You see, like the temperature 50, can you see here, 50, 100, 150, 200, 250. These are the constant temperature lines. So where this constant temperature line intersects a particular pressure line, okay, so there is a superheated vapor point. So at this point you can measure, you can note down rather the enthalpy as well as the entropy from the chart. So that is how you have to use the Mollier chart for the superheated region. Now for the wet region, so you will be given the dryness fraction. So you can see here, so this is the dryness fraction 0.95, because saturated liquid line, vapor line, sorry, this is the dryness fraction is 1. So below that you have the 0.9, 0.98, 97, 96, and then you have the 0.95 line. Suppose for a given pressure, for example, this some 0.2, maybe some pressure line here. So where it intersects 0.95, if you know the dryness fraction and pressure, So then you can locate this point and you can measure the note down the entropy and as well as the enthalpy. And for any isentropic process, suppose if you have a point in the superheated region here, if the process is isentropic, and after isentropic process, if the steam is in the wet region, then you can directly come down for the given pressure line and you can locate the point. And for the isenthalpic process, you have to go horizontally, because all horizontal lines are the isenthalpic lines and all vertical lines are the isentropic lines. So this chart, Mollier chart, is not of much use for this subject, pure substance chapter, but it will be of more use in the next subject, that is applied thermodynamics. Now let us study the property tables. Before that, let us understand what is the dryness fraction or the quality of steam. So this dryness fraction or quality of steam is applicable only for the wet steam, because saturated liquid is completely liquid, saturated vapor is completely dry steam. In between it is a two-phase mixture, so quality of which has to be measured or indicated by some term which is called as the dryness fraction, which is defined as the ratio of the mass of the dry steam to the total mass of the steam. Suppose if you have 1 kg, that is 1000 grams of water, if it is taken, now from saturated state, when it becomes saturated vapor, in between, suppose at a point 800 grams is converted to steam and remaining 200 is still in liquid state, then 800 by 1000, that is 0.8, is the quality of the steam. 0.8, or you can tell it as 80%. It is indicating that 80% of the total quantity is in vapor state and remaining 20% is in the liquid state. So it is denoted by the letter X, and it is given by mass of vapor to the total mass of the steam. So total mass of the steam is nothing but mass of liquid plus mass of vapor, so that is mf plus mg. So at the saturated liquid point there is no vapor, so this term becomes 0. So X is equal to 0. So saturated liquid point, so there is no mg, only mf is there, so this quantity becomes 0, so X becomes 0. At saturated vapor point, mf is 0, so it is completely vapor, so this mg and total quantity also same, so then it is X becomes equal to 1, and in between X is between 0 and 1. So X is equal to 0, saturated liquid, X is equal to 1, dry steam or saturated steam, and X between 0 and 1, it is a wet steam. Now let us go through few of the formulas which you are using for calculation purpose and for which you have to refer the property tables. Now if you consider a tank that contains a saturated liquid vapor mixture, means it is a two-phase region, let V be the total volume of the liquid vapor mixture of quality X, because whenever I say it is a two-phase mixture, so it should have a quality X. So your total volume of the container is V, out of which Vf is the volume of the saturated liquid and Vg is the volume of the saturated vapor, because it is a mixture, so some portion is liquid, some portion is vapor. So saturated liquid portion, the volume is Vf, capital Vf, and saturated vapor portion, the volume is Vg. And the corresponding masses, total mass is M, mass of the saturated liquid is Mf, and saturated vapor is Mg. Then you have total mass is equal to Mf plus Mg, and total volume is equal to Vf plus Vg. Now this Vf, capital Vf, can also be expressed as Mf into Vf, and capital Vg can be expressed as Mg into Vg, so that total volume you can express in terms of mass and specific volume of liquid as well as specific volume of saturated vapor, because specific volume is mass per unit mass. So Vf is meter cube per kg, so into mass of saturated liquid, so it gives the capital Vf. Similarly Mg into Vg, so that gives the capital Vg. Now the specific volume can be expressed as V is equal to 1 minus X into Vf plus X into Vg. Now you have to understand this formula. So you see X is the dryness fraction. So it indicates that so much quantity, percentage of total mixture is dry steam. So if it is X is equal to 0.8, means 80% is dry steam. So Vg, this is a specific volume of saturated vapor or dry steam, is occupying only 80% of the volume. So remaining 1 minus 0.8, that is 0.2 or 20%, is occupied by liquid. So you have to multiply 1 minus X with the Vf plus X into Vg to get the total specific volume of a saturated mixture. Try to understand this. 1 minus x, which is the liquid part, should be multiplied by the saturated liquid specific volume at saturated liquid Vf, and x, which is the dry stream, should be multiplied by the specific volume of saturated vapor Vg. Now similarly you can write this expression for entropy, enthalpy as well as internal energy. So S is equal to 1 minus x into Sf plus xhg in the same way. H is equal to 1 minus x into Hf plus x into Hg. U is equal to 1 minus x into Ef plus x into Ug. And all these formulas are applicable to wet steam only. Okay, these equations can also be written in this form, that is for the wet steam. You can write it as Vf plus x into Vfg. This is because you see you studied the property diagrams. Now if I take the TV diagram for example like this, so here it is the saturated liquid, here it is saturated vapor. So volume till here, so it is Vf, as all of you know. So this is Vf. Okay, and volume at this point till here from 0, it is Vg. So if it is completely dry steam or saturated vapor, then specific volume is Vg. If it is completely saturated liquid, specific volume is Vf. Suppose if it is in between here, right, so then you know that this length from here to here is Vfg. This is Vfg. Now for wet steam, if the point is here, so then enthalpy, total enthalpy is somewhere here, that is nothing but Vf till here plus this length, which is indicated by dryness fraction x into Vfg. So x into Vfg, this length is nothing but x into Vfg. So Vf plus x into Vfg is the specific volume of the two-phase mixture. So that is how you have to find out. If x becomes 1, then Vf plus Vfg, so that becomes directly equal to Vg. So this Vfg term is not there in the steam table. So Vfg you can calculate by formula Vfg is equal to V minus Vf, is equal to V minus Vf, because V is equal to Vf plus Vfg. But SFG and HFG terms are there, but Vfg term is not there in the table. So you can use this formula. Similarly, you can write the expression for enthalpy, internal energy and entropy in the same way. Hf plus x UHFG, Uf plus x UFG, and Sf plus x into SFG. So this is for wet steam. Okay, so all these expressions are applicable to wet steam. Suppose if the steam is dry, so then x becomes 1. So Vf plus x, Vfg, x is 1 here. So it becomes Vf plus Vfg. So that is directly can be obtained from the steam table as Vg. Though there is no term Vfg also, directly you can measure or mark or note down rather Vg. Similarly, H is equal to becomes Hg, and U becomes equal to Ug, and S becomes equal to Sg. Now if you observe the steam table, V, H and S terms are there, but U term, that is specific internal energy terms, are not there. In that case, you can find out using the formula U is equal to H minus PV. Okay, this I would have told before. Now I'll telling that. Now suppose if you want UF, so UF is equal to HF minus P into VF. Suppose if you want UFG, HFG minus P VFG, and HG is equal to HG minus P into VG. So internal energy terms are not there in the table what we are using. That is a thermodynamic data handbook by BT Nijaguna and BS Samaga. So in that book, that internal energy term column is not there. So, but you can find out using H minus PV formula. Now this is about the dry steam. Suppose if the steam is superheated, so the quality of the superheated steam is indicated by the term called as degree of superheat, which indicates that how above the temperature is from the saturation temperature. Now for example, at atmospheric pressure, as all of you know, the boiling point of steam is 100 degrees Celsius, that is saturation temperature is 100 degrees Celsius. Now the temperature of the steam at 1 atmospheric pressure is 150 degrees Celsius. So moment I come to know that the temperature of the steam at 1 atmosphere pressure is 150 degrees Celsius, I come to know that it is a superheated steam. Now superheated by what amount? So that is nothing but T super minus T saturation. So T super is 150, T saturation is 100. So 150 minus 100. So it is 50 degrees C of 50 degrees C is a degree of superheat at 1 atmosphere. That is very important. So if I am given degree of superheat, so I can find out what is the temperature of the superheated steam if I know the pressure, because I just have to add the T saturation temperature. So T super becomes delta T super plus T saturation because it goes to the other side, right? So there is just how you have to make use of these expressions. Now for a superheated steam, the expressions for specific volume is nothing but V super is equal to V sat into T super by T sat. This is based on the Charles law, constant pressure process. V super by V sat is equal to T super by T sat. So V1 by T1 is equal to V2 by T2 for a constant pressure process. So using that you have to find out V super by V saturation is equal to T super by T sat. So you can rewrite for V super. Now for H super, that is enthalpy of the superheated steam, you know that to become superheated, first it has to become dry steam or saturated vapor. So enthalpy of a dry steam or saturated vapor is Hg. Whatever the enthalpy increase further, because enthalpy is nothing but Cp into delta T, so further enthalpy of the superheated part is nothing but Cp into delta T is nothing but T super minus T saturation. Here Cp is nothing but the specific heat of the vapor. Very, very important, specific heat of vapor. So Cp dt. So Hg is enthalpy till saturated vapor. For superheated portion, the enthalpy change is Cp delta T or dt, which is nothing but T super minus T saturation. Similarly, the entropy of superheated steam S super is equal to Sg, that is entropy of the saturated vapor, plus entropy change from T saturation to T super. So that also whenever temperature change is there, so it is integration Cp dt by T. So after integration 1 by T integration is 1 ln T. If you apply the limit, it is T super by T sat. So here also Cp is nothing but specific heat of the superheated vapor. Okay. Okay, now let us study the measurement of steam quality. So there are two methods as per your syllabus to be discussed here. So first method is by using throttling calorimeter, and second one is by separating and throttling calorimeter. So let us discuss the measurement of steam by using throttling calorimeter. So here this is the steam main from where the sample has to be drawn using a sampling tube, and it is to be passed through a throttling valve. As the name implies, the throttling calorimeter, it should be passed through a throttling valve where expansion takes place. So after expansion, the pressure reduces and the quality of steam becomes either dry or superheated. Generally, we prefer the quality to be superheated for better accuracy in terms of measurement of Dryness fraction of the steam. Now the state before throttling is considered as 1 and state after throttling is considered as 2. So you should measure the pressure before throttling in order to know the property values from the steam table. And after throttling, as I told earlier, the temperature will be, the condition will be superheated. So you should measure its temperature as well as pressure using a differential manometer. And to know the mass flow rate of the steam, so the steam which is extracted and passing through this throttling valve should be condensed after throttling by passing it through a condenser, and condensate is collected. So by knowing the rate of collection of the condensate, you can find out what is the quantity of the steam flow rate into the throttling calorimeter. So now what happens here is, you know that the enthalpy before throttling, that is H1, is equal to enthalpy after throttling. H1 is equal to H2. So here H1, since it is a wet steam, as all of you know, H1 is nothing but HF1 plus X1 HFG1. Because it is wet steam, it has a quality of X1. So HF1 and HFG1 values, you can get it from the steam tables at pressure P1. And H2 you can get it from the superheated steam table. If it is superheated steam, or if it is a dry steam, you can get it from the dry steam tables. Okay, H2 is equal to Hg. For dry steam, H2 is equal to S super for superheated steam table. So more about this I will explain while solving the problem, how to get the value of H2 if it is dry and H2 if it is superheated. Now this is how the process is represented on TS. This is a TS diagram. Okay, TS and HS diagram. So this is the state of the steam before throttling. That means a wet steam sample being taken at state 1, and this is isenthalpic line. So after throttling you can see the pressure and temperature is marked here in the superheated region. So this is the state 2 superheated region. So if it is an enthalpy HS diagram or enthalpy entropy diagram or Mollier chart, so isenthalpic line is horizontal. So this is the state 1 at pressure P1 with the dryness fraction X1, and state 2 is in the superheated region with pressure P2 and temperature T2. Okay, so H2 you can obtain from the steam tables. At pressure P1 you can find out H1, HF1 and HFG1. So H1 is nothing but HF1 plus X1 HFG1. So X1 is nothing but H2 minus HF1 divided by HFG1. So this is how you have to calculate the steam dryness fraction using throttling calorimeter. Now it's a combined separating and throttling calorimeter has two parts. First part is the separating part and second part is the throttling part. So let me explain you about the separating part first. So this is the steam main through which steam is passing. This is the sampling tube as earlier. So now steam is extracted and passed through a stop valve. So condition of steam before it is passed through the separating unit is the 1. Okay, pressure P1, temperature T1. Now it is passed through a separator unit here. So here some mesh type structure is there, fine mesh. So steam is made to impinge on that surface so that the suspended water particles are separated and they are collected at the bottom. So by which you can find out what is M1 or MF, the mass of liquid. So mass of steam is now going through the throttling valve. So here you see dryness fraction of measured using this separating calorimeter is nothing but mass of steam going to here, that is M2 divided by M1 plus M2, total mass of steam, because M is nothing but, you see, this M is what is entering into the separating part. M1 is separated as water particles separated as and collected at the bottom, and M2 is the steam entering into the throttling calorimeter. So total steam M is equal to M1 plus M2. So M2 divided by M1 plus M2 is the dryness fraction calculated using the separating calorimeter as X1. Now here the condition of the steam before throttling valve is 2, pressure is same, both are P1 itself. Okay, so there is no change in pressure in separating calorimeter. So only after throttling the pressure changes to P3 and temperature changes to T3, and this differential pressure is measured using a manometer and is calculated as P2. Now throttling calorimeter I already explained. So here H2 is equal to H3, right? So in order to know the condensate or steam M2 passing to throttling calorimeter, so it has to pass through a condenser. So you can calculate here what is the steam passing through the throttling calorimeter M2. So now you have got the two dryness fraction values. One is X1 using separating calorimeter and X2 using throttling calorimeter. So X1 is into X2 is the dryness fraction of the steam. So this, for better accuracy, you are using separating calorimeter part as well as the throttling calorimeter. Two dryness fraction values you have to find out, and you have to multiply those two to get the dryness fraction of the steam. So your process 1-2 represents the separation from the wet sample steam at constant pressure P1, and 2 to 3 is just explanation. Throttling pressure to P2 and T3 being the temperature measured. H3 is the enthalpy of the superheated steam. So H3, as I told you earlier in the throttling calorimeter, can be measured directly from the table, and H2 is nothing but HF2 plus X2 HFG2. So this will give the value of X2. Okay, and the X1 can be found out. The X1 can be found out from the separating part. As I told you earlier, total mass entering into the sampling tube is M1 plus M2, where M1 is the liquid part, M2 is the vapor part. So M2 divided by M1 plus M2 is the dryness fraction measured using separating calorimeter, whereas X2 is the dryness fraction measured using throttling calorimeter, and final dryness fraction X is equal to X1 into X2. So this is how the dryness fraction is measured using combined separating and throttling calorimeter. So with this I conclude the theory portion of the pure substance under module 4, and will continue in my further lecturings few numericals. Okay, thank you.